Thank you very much. I'm very excited and grateful to be giving the first talk of the week. I hope it'll be a good warm-up talk, because we're literally going to be looking at rectangles filled with zeros and ones, and we'll figure out whether they are balanced or not. And I'll explain in a moment what that means. Let me just mention that this is joint work with Jeff Shallit. I was his postdoc last academic year in Waterloo, Canada. But actually, we wrote this paper just a couple of weeks ago, actually around the time that I was here at CM for the very first time at combinatorics, automata, number theory. And in fact, the solution of the problem will mostly be based on automata. If you don't know automata, don't worry, I'll just give you the vibes of it. And also the problem is actually equivalent to a problem in Diophantine approximation and distribution mod 1. That's not in the paper, but I'll tell you at the end of this talk. So stay tuned, and let's start with just our very favorite sequence of integers, which are, of course, the Fibonacci numbers. And I want to plug a little game that some of us came up with when we were here a month ago, which is the table tennis Fibonacci game. It has a lot of silly rules, but the point is, we're not very good at table tennis, so we need to set ourselves goals for how many ball exchanges we need to do without making a mistake. And it turns out, setting yourself the next goal to be the goal from before plus the goal from one before is actually a really good way to set yourself goals. And if you start with 1 and 2, you get the Fibonacci numbers, so that's just a reminder of why we love the Fibonacci numbers. And I want to point out one property of the Fibonacci numbers, which is that every integer, every positive integer, can be represented as the sum of Fibonacci numbers. So for those who don't know Ostrovsky representation or Tekendorf representation, let's just do one example. Let's look at 17, and let's try to represent it as a sum of Fibonacci numbers. Let's do the greedy thing. So what's the largest one in the list that fits into 17? Well, it's 13. How much do we need? We need 4. 4 is not on the list, but 3 plus 1 works. So, well, we can always do the greedy thing. We don't need these here. And then if we do the greedy thing, we always get a unique representation. And so here we could write this is the 7th Fibonacci number plus the 4th Fibonacci number plus the 2nd Fibonacci number. And if we write this in digit representation, then we write, well, what's the smallest one we could have? F2. We do have F2. We do not have F3. We do have F4. No F5. No F6. 1 F7. And that's the digit representation in Fibonacci representation. And this will be important later. But for now, we've talked about Fibonacci numbers. But my talk's actually about the Fibonacci word. So what's the Fibonacci word? Okay. The Fibonacci word is, can you read this? Is this fine? Okay. The Fibonacci word is a sequence of zeros and ones. And let's define it. I think a reasonable way to start is with 0. And then we want to sequence with zeros and ones. So actually, I think 0, 1 is a reasonable way to start. And then we do the most Fibonacci thing we can think of. We just take the previous block and we append the one before. And then we take the previous block and we append the one before. And again, the previous one, append the one before. 0, 1, 0. And then you can keep doing this, so then we get 0, 1, 0, 0, 1. And of course, this defines a sequence which is called the infinite Fibonacci word for obvious reasons. Yeah, that's what I'll be talking about. However, this is not the definition that we'll be using, because there are many different definitions. And in fact, this word is also a Sturmian word. Okay. And it's, of course, related to the golden ratio. In fact, the way we'll define it is with this phi prime, which is 2 minus the golden ratio, which is roughly 0.38. It's just a definition thing. Think of it as the golden ratio. And what we can do, so I've drawn here the unit interval and stuck it together. So here is 0 and 1, and then here is a half, 3/4. And we can do irrational rotations by this phi prime. Oh, sorry. So, oops, what's going on? Sorry. Oh, okay, I don't know. Usually this should change by just 1. Oh, I tested it like 10 times, but now it's annoying me. I'm sorry. So, oh, come on. Okay, I'm really sorry. Okay, so we have the unit circle, and then we do these rational rotations, and then I draw, you'll see it in a moment, hopefully, this interval that's red, and every time we land in there, yeah, I'm really sorry, I don't know what happened. So we do, oh God, yeah. So now I've rotated 10 times, and first we landed like here, and then here, and then here, and so here we're at the 10 times phi prime. This is in the red area, and therefore the last digit that we recorded was a 1. And then after that, we keep, oh no, we keep rotating. Oh no. Yes, okay, so we keep rotating, and every time we land in the red area, we record a 1, and when we end up in the white area, we record a 0, and it turns out that the sequence we get is exactly the Fibonacci sequence. And I'm not doing the proof, but why is it plausible that these are the same sequences? Well, every time you get to a Fibonacci number, so for example, when we get to 21, then we get really, really close to 0, because the Fibonacci numbers correspond to the best approximations of phi, and then we get really, really close to 0, which means that essentially we start all over again. And that's exactly what we did here. Every time we got, these have lengths of Fibonacci, and every time we get to the end, we start all over again. Okay, and so actually we're gonna deal with this sequence thinking about it this way. And so we can write down the definition as A1, A2, A3, and so on. So AI is the floor of I plus 1 phi prime minus floor of I phi prime, because, well, this is either going to be the same number, we get 0, or this is 1 larger, then we get 1, and it's 1 larger exactly if we hop over the integer as we go from I to I plus 1, which is exactly when we're in the red area, because then we rotate by 1 and we get over the integer. Okay. So this was the Fibonacci word, and what does balanced mean? Balanced is actually a property of the Fibonacci word. Namely, we can look at blocks of the same length in this word. For example, if we look at blocks of length 5, here is a block of length 5. How many 1s does it have? Which weight does it have? It has 2 1s. And what about this block? Well, 1, 2, 3, 4, 5. It's also got 2 1s in it. Can we find a block of length 5 with a different number of 1s in it? Yes, here. Actually, we've just got 1. And it turns out, if you check all the blocks of length 5, you will always have either weight 1 or weight 2. And so we say the blocks of length 5 are balanced. And it turns out you can do that for any length k, and you will always be in a balanced situation. So you'll have exactly 2 possible values. And we can also quickly prove that, in fact, all the blocks of length k are balanced. Let's briefly do that, because it will be important later. So let's look at some block starting at index I. And we can just add the digits up to I plus k minus 1. That's k of them. And if you plug in the definition, then you get a lot of telescoping, And what's left is the largest thing coming from here, I plus k minus 1 plus 1, phi prime. And then everything telescopes away. And the last thing is from the smallest one, I phi prime. And if you ignore the floors, then this is k times phi prime. And if you check the details, you will see that you either get exactly the floor of k times phi prime, or you might get one more in case that here you sort of hopped over the integer. So if the fractional part, that's the fractional part of I phi prime plus the fractional part of k phi prime, if this is at least 1, then you need to add 1. And so, well, this is fixed. This is maybe plus 1, so we are balanced. Okay, so this is a basic known property of the Fibonacci word. And what we want to do today is look at rectangles. Because other people have also in the past aligned the Fibonacci word in a rectangle in the Hankel matrix. So the first row is the Fibonacci word, and then every time we go down, we shift to the left, so we get these diagonals with the same value. Okay, and now we could of course ask, are the rectangles balanced? For example, if we look at rectangles of size 2 by 3, here we've got 2 ones. How about a different one here? We've also got 2 ones. Can we find a rectangle with a different number of ones? Ah, yes, right here. 3 ones. So that's still balanced, right? 2 different values. And in fact, if you check all the rectangles that are 2 by 3, it's pretty easy to check that you will always have either 2 ones or 3 ones. So we say that the 2 by 3 rectangles are balanced. Let's look at some different size. Say 2 by 4. So here we've got 3 ones. Here we've got, oh no. Here we've got, can we find a different number? At the end, we've got 4 ones. Thank you. Can we find one? I think we should actually be able to find one with just 2 ones. Yes, right here. Ooh, that's just 2 ones. So this is not balanced, right? Because we have 3 different values. Yeah, and so we say that the 2 by 4 rectangles are not balanced. And of course, now we want to know, hopefully, well, which ones are balanced and which ones are not balanced. And in a very recent paper, Anselmo, Ejamaresi, Madonia, and Salmi proved a special case, namely if the maximum of your side lengths, mn, happens to be a Fibonacci number, then you know you are in the balanced situation. And this fits, because here 3 is a Fibonacci number, 4 is not a Fibonacci number. Their statement is not if and only if, but I mean, this checks out. But our goal today is actually to characterize exactly which rectangles are balanced and which ones are not. Okay. And the solution will be based on automata, because it turns out the Fibonacci word is a Fibonacci automatic sequence. If you don't know what that is, don't worry, it means you can compute it from if you have Fibonacci representations. And we will also use the software Walnut, which makes automata for you, and it can prove theorems for you automatically. And this is not an introduction to Walnut, but I do want to give you the vibes, and I also want to show you how it works so that you're not scared, because I was quite intimidated, but it's really easy to use. And the way you find it, you can just Google it. You can Google Shallit, so it's hosted on Jeff Shallit's website, Shallit Walnut. And you get to this website. It's a really good starting point. So Walnut was programmed by several people, in particular Hamoon Musabi, and mostly students of Jess. And you can even use it online without downloading. So you just click this link, and then you need to wait a couple of seconds. And in the meantime, I'll just explain roughly what automata are. So they are like the simplest machines that you can think of. They have a finite number of states, and then you can input things in their digit representation. For example, if you wanted to input 17, you could feed the machine this string of digits. It will go through several states, and once you're done, it will end up in the state, and it will either output something, or it will tell you, yes, your input was accepted, 17 is accepted, or no, sorry, not accepted. And Walnut lets you type in just statements with restrictions, and it just builds the corresponding automata for you. Here we are. So then you hit New, Walnut, and you wait just a moment. Okay. And I'll just show you how it works. Let's define an automaton. We type def, define. I'm going to call the automaton, can you read this? Yes. Greater than 2. And here's where we're going to define it. We have to tell it how we want to input things. And of course, today we want Fibonacci numbers. So we type in question mark, MSD, most significant digit first, fib for Fibonacci. And I want numbers to be accepted that are greater than 2. And then I hit evaluate, it does something, and then usually a new cell appears, but not now. Okay, then we can just say, show me this automaton that I defined, and here it is. Okay, so people have programmed these algorithms that are already known, and here we could input our number 17, so we would read the most significant digit first, 1, so we would go over here, so we always start in this state, read 1, then we read 0, we read 0, read 1, read 0, read 1, and we would end up in this double circle state, which means that it's accepted, and indeed 17 is greater than 2. So yeah, that's roughly, if you've not seen this before, just take the vibes, and yeah. So you can type in statements, but of course there are restrictions because it doesn't solve all of maths for you. And one important restriction is that you can type in statements, like you can type in statements about integers, you can add integers, you can multiply integers by constants, you can say something for all n there exists a k, and so on, but you cannot multiply variables. And that's important. Because now we're going to look at our problem. So our goal is to type into Walnut what is balanced, and then we want Walnut to just tell us, well, this is balanced. Okay. So I've written down what the rectangles look like. We want to figure out how many ones there are. So we want to sum over these matrices. Now, the obvious thing to do would be to somehow try and translate this into Walnut and like sum over these rectangles in Walnut. But if you were able to sum over rectangles, then you would also be able to do multiplication, right? But we can't do multiplication, so that's not going to work. So we need a trick. And once you see the trick, it's so obvious, but it took us a bit to find the trick. The trick is the following. Okay, what we think is, what happens if instead of looking at the rectangle at index I, we slide over to the next rectangle, starting at the next index. So we're going to go from this whole rectangle to the next one. And what happened? We lost this column, but we gained a new column. By how much may the value have changed? Well, we know that the blocks are balanced. So the one we lost and the one we gained either have the same value, so nothing happened, or we increased by 1, or we decreased by 1. So if we define this difference sequence, say delta, mn, and it tells you how do you change as you go from I to I plus 1, then this sequence will be in 0, -1, or 1. And the good thing is that this is something you can deal with Walnut, because it's not a rectangle, it's just 2 blocks. You can literally write down the formula for it. It contains floors. In a paper, Jeffrey Shallit and Zoricic already figured out how to deal with floors if you have a quadratic irrational multiplied by an integer. That's something we can do. And then you can just type in your statement, like, right, sorry, now we can deal with this different sequence, but how does it help us with the rectangles? Well, we wanted to know whether they are balanced, so whether we ever change by more than one. And of course, the only way we can change by more than one is if somewhere along the way we increase by one, then maybe for a while nothing happens, and then we increase by one again. Or we decrease by one, nothing happens, and then we decrease by one. If something like this shows up, then we're in the not balanced situation. Otherwise, we were just going up and down, and we were balanced. Right. Pretty simple, and in fact, you can translate this into something that Walnut understands. It's really not many lines of code. The first lines just establish this floor thing, and then you just type in the statement whether you have this block or not. And so I'm going to copy this into Walnut, evaluate, and then it does take a couple of seconds. It builds these intermediate automata in the background. Here, this one has like 1,000 states. Yeah, we're not displaying them. But I think now it's done. Yeah, here we are. And then show me, I called it bal, for balanced. And this is the answer to your question. So if you have a pair of lengths, you can represent n and m in Fibonacci representation. You can feed it into the automaton. That's why we always have 2 digits, because we're reading 2 numbers in parallel. You can follow it around. If somewhere along the way you want to go in a way that's not, where you don't have an arrow, it means that you're not accepted. But if you can go through the automaton, end up in a double circle state, then we are in the balanced situation. Now, you look a bit unhappy because this is a very English answer, but I actually sat down and tried to figure out what this means in English. And to do that, I restricted the automaton just to m less or equal to n. Then it becomes smaller. And then I colored in the important paths where things happened, and I stared at it really badly, and I got it wrong many times. But finally, this is the characterization. You don't need to read it, because I'll just show you a couple of examples that explains which numbers are exactly accepted. So the first case is just trivial cases. If your rectangles are empty or one-dimensional, then of course we are balanced. The second 2 cases are if your smaller number happens to be a Fibonacci number, for example, f7, then essentially, usually you are balanced. So if n contains f7, then you can have anything and you are balanced. But if n does not contain f7, then there is some parity restriction. So the next larger one that shows up has to have the same parity. So you'll have like, if you have f11 and anything else, then you are also balanced. Okay, and the last 2 cases, D, E, are where m is your smaller number. Again, say this time it has a couple more digits. And then you are in the balanced situation if n only has large digits. So there has to be this divide where you can have large digits here, but nothing here. And there is this edge case where actually you exactly have this overlap, and then again you have some parity restriction. So I think different parity, so f10 would be fine. Okay, so that's the full characterization, what the automaton tells you, and now we know which rectangles are balanced and which ones are not. How does this relate to Diophantine approximation? Well, maybe this already sort of gives you hope that there is some reason behind this, because only having large digits means that n times phi prime is relatively close to 0, because you've only got the large convergence. So now let's look at what our problem is if we actually think about distribution mode 1. And what we're going to do is actually write down the sum that we're interested in. Because with Walnut, we avoided computing the rectangles because that was bad, but now let's actually do it. Let's write down what the sum is. And luckily, we already have a formula for blocks, so for columns. So we could just add over the columns, sum over the columns. And I think I'm going to do this here. Yeah. So the sum over the columns is, I'm not doing the details, you take this and you sum, and then you get n times m5 floor, plus, this comes from these guys, and then you need to deal with these fractional parts. And if you deal with them, you get the sum over k goes from 0 to n minus 1, and then every time you need to check whether the fractional part of I plus k phi prime, whether this fractional part is large, namely whether it's in the interval 1 minus fractional part m phi prime 1. And if it's in there, you count it. And this is the exact formula. So if we want to know whether the rectangles are balanced, well, this is fixed, so we only need to know whether this sum can vary by more than 1. And this is really just about counting fractional parts, which means we can go back to my animation, which this time will hopefully work, because I've fixed my keyboard. Okay, so this is the unit circle. N, lovely, gives us these points. And N determines how many points we look at, how many we consider. And then M tells us how large the interval is, because it's m times phi and then take the fractional part. So for example, here we have this interval length. And then so there's one step you need to think, but you will see that to check whether this is balanced, you need to look at all the shifts of this interval and see how many points there are. So here we've got 2 points, 1 point, 2 points, 1 point. This is all balanced until we get to here, no points. So we have no points, 2 points, so we are not balanced. And indeed, the pair, Walnut says that 11, 16 is not balanced. So this is the translation. And I don't know, maybe people who know Diophantine approximation and Ostrowski digits, maybe this is somehow obvious. I think certain cases are obvious. So if your larger number is a Fibonacci number, then of course your interval is going to be really, really small. So then of course you have 0 or 1 points. But the other cases seem to be a little bit messy. I mean, this was a characterization, and I think it's pretty nice that you could just type it into Walnut. It does all the work for you, and this is the answer. And also, well, the problem is equivalent to these rectangles, and that's all I wanted to say. So thank you very much, and I hope to play the Fibonacci table tennis game later this week.
All right, thank you, Ingrid. Are there any questions for the speaker?
Thank you for a nice talk. And today you mentioned one balanced. Yes. So my question is about two balanced. Is it possible?
Right. So two balanced would be if we allow 3 different values, for example. Yeah. So we started looking into that. It's a good question. I don't know the answer off the top of my head. So in this way of thinking about it, you would just you would allow a slightly bigger discrepancy. And if you think about whether you can type it into Walnut, so then you would, because then it would be more complicated, right? Here, the trick was that it's very easy to figure out whether you leave this or not. So if we had, if we were allowed to vary by 2, I'll have to think about it. I've already thought about it, but I've forgotten. Yeah. Thank you.
Thank you.
Is there another question? Oh, there's one at the back. I won't trust myself to throw the microphone.
Yeah, so thank you very much. So in the same way that you took the Fibonacci word to make a two-dimensional Hankel matrix, you could presumably take the two-dimensional Hankel matrix and turn it into a three-dimensional Hankel 3D matrix. Not sure what you'd call that. Would your method... Because I can't see an immediate result or reason why it wouldn't then apply to cuboids. Or your method, anyway.
Right, well, then your changes would be two-dimensional, right?
Yeah.
So then you can't really do the same trick because you can't compute the changes.
But wouldn't the change be just the difference between the sum of the digits in the sort of slice you lost and then the slice you gained?
In the case that, yes, so in the case that the changes are rectangles that are balanced.
You could then maybe do something.
Then you already know that they only have two values.
Just an interesting
thank you.
problem.
I'm too stressed right now. I'll think about it later. Thank you.
Thank you.
All right, thank you. Is there another question? Somewhere? Oh, down there. I feel like there's some coordinated effort to make me go up and down the stairs.
Thank you. And what about other Sturmian sequences?
Other Sturmian sequences. So if you have quadratic irrationals, then you can do exactly the same thing because it has been implemented in Walnut for other, for all quadratic irrationals. If you have not quadratic irrationals, then I think you can't do it in Walnut because there's no way to deal with them. But that's something I want to look into. Like I think there should be a similar property for, at least for badly approximable numbers. I don't know what happens for other numbers.
Yes, you can also add a shift.
And a shift.
Intercept.
How do you add a shift?
So phi prime plus theta. You add plus...
Here?
Plus, yeah. No parentheses. Just... Okay, and the plus theta are the same.
Theta. Okay. Well, I think that isn't that equivalent then the question? Because it just, in this sense here, you just, everything, you need to look at, oh, sorry. You need to look at all the shifts anyways.
Okay.
So I'm not 100% sure. I might be saying nonsense, but I'm not sure. I'm wondering, doesn't that just change the beginning of the sequence? Okay, thank you. Okay. I don't know.
One question: does anybody study the, say, proportion of balanced rectangles? For instance, among all the rectangles, so you fix M and N.
Yes.
Just maybe for Fibonacci word.
For what word?
Just for Fibonacci word.
For Fibonacci word. Yes, actually that's in our paper. Jeff gave a lower bound for the number of balanced rectangles, I think. Yeah.
For fixed MN.
For... Oh, then I misunderstood the question.
So you fixed the scale of the rectangle and ask how frequent rectangle is balanced.
So you fix MN.
For instance, you fix MN. You fix a large part of your table. You calculate all the rectangles in this table, and you look for the quotient of balanced rectangle, of number of balanced rectangle to the whole number of rectangles. Does anybody work with these statistics?
I'm not aware, but also I'm a little bit confused because, so we said balanced if there exist exactly two possibilities for the weights of rectangles. So I'm not quite sure what your question is.
Okay. Sorry.
We had another question down here. Sorry, let's squeeze through.
I'm sure that Jeff must have looked at the question, but you know that in computer science you've got this big problem that if you take the so-called Kolakowski sequence to determine whether it's balanced.
Sorry, which sequence?
Okay, so there is a sequence which is called the Kolakowski sequence.
Okay, I'm not.
And well, I'm sure that Jeff must have looked at it. The question I'm asking is whether, so if you just input a one-dimensional sequence, Walnut is able to tell you whether it's balanced or not, or do you need this sequence to be automatic in the first place?
Well, I think to deal with the sequence, I would think it has to be automatic.
For Walnut to work, you mean?
For
Walnut.
For deal with it in Walnut, yeah.
Okay.
How is Walnut going to know anything about the sequence if it doesn't know it?
You can define it otherwise,
but you define. Maybe there is a trick. I don't know. I only used Walnut for the first time in this paper, so
okay.
Yeah.
All right, is there another question? I'm just going to work my way out of the aisle here. No, if there are no further questions, then let's thank Ingrid again.